seen installed in many places, hotels and so on. And we try to do a very simple experiment in the lab. So we bought one of the lockers as it is from the market. So I will not, for the purpose of privacy, let's not discuss the name of the locker, but the company of the locker, and it's a very famous company, by the way. So we buy that, and we all know that suppose it has got like an n-digit pin. So maybe in this case it's a 6-digit pin, and every pin, right, can take typically like 0 to, or like 1 to 9 values, and you can probably anticipate that how many possible combinations can be there to unlock this locker. So that is quite large. But if you are aware of how it is implemented, so we try to kind of do a simple experiment. We opened the in front part of the locker, and then we found out that yes, there are 2 pins as it is shown in the below diagram. One is a ground pin and the other one is a reset pin. It turns out that if I just short these 2 wires, then the pin is zeroized. So after that, you just press 0, 0, 0, 0, 0, and the locker opens. So this is a very simple example to show that what the designer intended and what an attacker can do. So the attacker didn't kind of, like really break the protocol or the technique which was implemented by the locker designer, but just found out another way of bypassing the protection which the designer had implemented. So there are several, this is a very simple example, but there are similarly several examples which can be probably cited from our experience, where we show that if there can be many pitfalls in the design principles. Like, for example, one of the very common pitfalls is not to test your cryptographic design in a proper manner, and that can lead to attacks, and that can lead to glaring vulnerabilities which often do not challenge the mathematical principles of the cipher or the cryptographic protocol, but tries to just find out another way of breaking into your system. So, so in order to do these kind of experiments of attacks and countermeasures, we set this lab in our department or institute, which we called as Secured Embedded Architecture Lab, for probably the last 10 years or so. And we have like few, like faculty members and also like research scholars and postdocs who are working in several areas of design, attacks, and countermeasures. And we essentially have got, I mean, since our work also requires a lot of practical evaluations, like in side channel attacks, IoT security, cyber physical system security, hardware forensics, we have, I would say, a decent amount of experimental base of doing these kind of experiments. So that was a rough, like background on to our lab at IIT KGP, and now we can really get into the topic. So I will be talking about in today's discussion about Internet of Things, and we all know that IoTs essentially are a very promising next generation networks, which tries to extend today's internet much further by connecting a wide spectrum of devices. It is estimated that by around a few years, there will be billions of devices which are being connected, and so potentially IoTs can revolutionize the quality of life. But the point is, like, which gives us a lot of opportunities, is in terms of the fact that many of these commercial IoT devices lack security measures and therefore can have catastrophic consequences to mankind. In the Indian context, also, IoTs has got very promising applications in terms of water control, food control, governance, drug controls, and so on. But again, the baseline is that we need to integrate security into the IoT by developing novel secure protocols for interactions of multiple components, which otherwise can leave menacing threats. So therefore, right, I mean, let me try to give an example where side channels are, side channels are relevant in the IoT context. So there was a very nice paper which was published in IEEE Symposium on Security and Privacy, which is one of the top conferences in security, where the title of the talk was, or the paper was, IoT goes nuclear, creating a Zigbee chain reaction. So I will try to give an overview behind this attack. So this attack was demonstrated in Israel, And you can see that it basically attacks what are called as a smart bulbs. So the smart bulbs essentially are nothing but our normal bulbs with some amount of intelligence, in the sense like depending upon your like mood, you can apparently control the lighting of the bulbs, and you can actually kind of create an ambience according to your temperament at that time. So there is a very famous, for example, bulb or smart bulb which is being sold by Philips, and that is called as Philips Hue bulbs. So in this particular attack, they try to do a very interesting attack combination on these bulbs. So as they are smart, like they have some kind of authentication check in the fact that you have to be whitelisted beforehand to be able to control these bulbs. And that is obvious because you do not want, right, at the end of the day, your neighbor to control your bulbs, right? Because you want you to control the bulbs. So there is an amount of authentication being in place in these bulbs. And they also have something which is called as a proximity check, which means that you are expected to control these bulbs within a distance. So you cannot control these bulbs from a very far location. So what the attackers did first is that they wanted to see that whether they can update the firmware where this proximity check is removed. But then you have to update the firmware, and you cannot, of course, you can write the firmware because it is on a standard processor. So you can create a corresponding firmware to that, but you cannot sort of install the or make the firmware run on this particular hardware simply because there is an authentication check, or I would say like a MAC check, which is being done by this system. So there is a secret key, and the secret key is a 128-bit secret key, which basically does something which is a simple, what is called as a CBC MAC. And that is used to kind of verify whether the firmware is authenticated or not. So therefore, they wanted to forge the firmware. And if you really want to forge the firmware, then one easy way would be to know the secret key. But then the secret key is a 128-bit secret key. And if you are using something like an AES CCM algorithm, then you do not probably expect that you will find out an easy hack to get the key. So therefore, the attackers tried to resort to side channel attacks, and they did something which is called as a correlation power analysis, which I will be trying to talk a little bit in my talk, in my presentation. So they did this attack, which is called as a CPA. So you can see this power trace. And from the power trace, after doing some statistical analysis, they were able to recover the 128-bit secret key. Now, once you recover the 128-bit secret key, you can actually update the corresponding bulb's firmware where the proximity check is bypassed. And also they found out, and this is a very strange coincidence you can say, but the bulb designers probably didn't anticipate that somebody will come up with this CPA technique to recover the key. So when they install the bulb in the offices, you can see that there is a diagram at the top which shows that the offices are from top security companies like RSA, EMC Square, Oracle, and so on. So they found out that all the bulbs in a particular office premise had the same secret key. So therefore, right, once you recover one key and you update its firmware, you can potentially kind of update all of their firmwares one by one. So they did a sort of a, I would say, like what is called as a nuclear chain reaction. And then they eventually controlled all the bulbs. And then they gave a very interesting demonstration, which you can also see in YouTube, where apparently you can run, what they did was they had some drones which were flying and they were controlling the bulbs from a distance, and they were displaying an SOS signal. So it was just to kind of show that all the smart bulbs in that office premise were controlled and were possessed by the attackers. So this is something that you definitely not want to have, right, in an IoT scenario, but it also shows that the power of control and command, if it is combined with some techniques like maybe, like physical attacks on the things, then it can really give very devastating attack surfaces, which can be, which we would like to prevent against. So therefore, right, this brings me to my, like this particular slide, which says that, yes, we need strong cryptographic algorithms, but strong cryptographic algorithms are just the beginning. We also need a very strong cryptographic engineering. So if you take, for example, a smart card on which you have got a nice cryptographic algorithm protecting your secret key. So when you are normally exchanging your inputs and outputs, then there is a level of security which is guaranteed by the mathematical algorithm. However, it may also happen in the real world, as I showed, that you are also revealing the power consumption, say, of the computation or during the computation, and that power consumption can trivially leak the key. So it may happen that if you do not have proper defenses being implemented in your crypto algorithm or in crypto implementation, then it can reveal the key in a very trivial manner by just revealing a side channel information. So then the question is, what are side channels? Well, side channels are, I would say, like covert channels which leak information which the designers of the crypto algorithm did not consider. So it could be any information source. Okay, so it is not that it is only restricted to power consumption or EM radiations, but it can be anything for that matter. It could be timing of your computation. It could be, like a strange, like combination of when you are implementing a crypto algorithm on an advanced microprocessor, there are several optimizations being in place like speculative execution, cache memories, branch predictions, which can open up side channels for your cryptographic computation. So I would say rather that these are sources where, in a general sense, through which information is leaked because of the implementation. So it could be, like because of an optimization which you are doing in your crypto implementation. It could be a simple if-else statement in your programming language, and if that if-else statement depends upon a secret key or a variable which is derived from the secret key, then you can potentially open up Pandora's box for side channel adversaries. So I will be trying to kind of restricting to a power side channel setup, or I would say an EM side channel setup, which we have in an ITKGP laboratory. So here is a very simple demonstration of that. So there are typically 3 parts to this setup. You have got a PC on which you are running your crypto engine. So it could be, like a symmetric algorithm, asymmetric algorithm, or anything for that matter. And then whenever it is being computing, so what you are doing is you have got the crypto, you have got the crypto engine which basically operates on this FPGA board or maybe the hardware on which you are operating. And then there is a PC through which you can actually send your inputs. Like you can send the plain text for encryption, you can send the ciphertext for decryption and so on. The crypto engine is actually running on this particular FPGA. So it could be a symmetric algorithm or an asymmetric algorithm. So normally when you send the plain text, you get back the ciphertext and that is being stored in the PC. But in this case, we are also observing the corresponding, say, like power consumption of this device whenever they are doing encryption. So for example, if you are doing 10,000 encryptions, then you have got 10,000 power traces, which is being, like amplified suitably and being recorded by the oscilloscope. And this data is also being stored in the PC simultaneously. So there is a synchronization which is involved. So you, as an attacker, you get not only the plain text ciphertext, or maybe you just get the ciphertext, but you also get along with it a corresponding power trace. So you get the power trace, and the question is now, can you recover the secret? So this was essentially initiated by a very famous paper by Paul Kocher, published in Crypto in around 1995, 1996. And that essentially set the context of what are called as side channel attacks. So these are some, snapshots of the real setup here. So, so therefore, right, power attacks essentially typically are of 2 types. The simple technique is what is called as simple power analysis, or SPA. And there is another technique which is more sophisticated. It is called as the differential power attack, or DPA. So in a simple power attack, the fact which is exploited is that the power consumption at an instance of time is a function of the operation being carried out by the device. So I will try to give an example here. Like suppose you are implementing, like an RSA kind of operation where you are, like raising maybe an input to some exponent, and that exponent is, say, a secret. Okay, so suppose you are doing y power of d modulo n, and this d is something which you would like to kind of prevent from going to the adversary simply because it is your private key. So how do you implement y power of d? Of course, like you would not like to multiply yd times because that would be very inefficient. So what you typically do is you apply an optimization technique from algorithms, which is implement y power of d by engaging an algorithm, which is commonly called as the square and multiply algorithm. So what is a square and multiply algorithm? In a square and multiply algorithm, you take the exponent d and you encode it as a binary strings of 0 and 1. So now what you do in a very naive algorithm is you always do a squaring operation, and you also conditionally do a multiplication operation. So you basically do a squaring always, and you also do a multiplication when the exponent bit is 1. So now you see that you are doing two operations. You are doing a squaring and you are doing a multiplication. Okay. And what simple power attack tells you, or this particular line tells you, is that the power consumption at an instance of time is a function of the operation. That means the power consumption for squaring and the power consumption for multiplication are different. So that is what you would like to pick up in your side channel trace. And the idea is that if you find out differences, then you know now that a multiplication is being done compared to other instances when a squaring is being done. And that essentially opens up the avenue for side channel attacks, or what is called as simple power analysis, or abbreviated as SPA. Now, there are many ways in which you can protect against this SPA. For example, a naive way would be, let me do an always square and multiply algorithm. There are yet other more sophisticated algorithms like Montgomery ladder and so on, which I am not going for the sake of time. But the point is, right, there are ways of protecting against a simple power attack. But there is another stronger form of adversary, which is called as DPA, or differential power analysis. So here, the fact which is exploited is even more fundamental. Here, you try to kind of exploit the fact that the power consumption of the same operation at different instance of time actually depends upon the underlying data which is being processed. So that means whether you are processing a 0 or whether you are processing a 1 is actually different, and that leaks information which is exploited by a DPA adversary. So that implies that even if you are protecting against a simple power attack or an SPA, you are still vulnerable against a DPA attack. And that essentially leads us to a more sophisticated attack method, and therefore we need even more, I would say, more interesting ways of protecting against DPA. So how does simple power analysis work? So let me try to kind of, I already tried to kind of talk about the basic technique of an SPA. So the SPA typically works on power traces. So you can see that it will directly interpret the power consumption of the device. It will look for the operation which is taking place and also the secret key. And it will basically take the trace. The trace is nothing but a set of power consumptions across a cryptographic process. So as an example, say that suppose you have got a 1 millisecond operation where you are, it's basically a cryptographic computation which you are doing. You also sample that operation at different instances. So suppose you are sampling it at 5 megahertz, which will imply that you have got a trace which has got 5,000 points. So a simple power attack will typically work with few traces. So the trace number could be something like maybe 1, 2, or maybe few hundred, okay, like maybe 100. So there are very interesting examples of simple power attacks which has been done. One of the most, I would say, like popular example of SPA is done on what is called as the key lock cipher. So the key lock cipher is essentially the cipher which is often implemented on your car lock. Like if you see that the lock that you have in a typical RKE or remoteless key entry of the car, it engages an algorithm which is called as a key lock cipher. It's a very simple algorithm. Initially, they wanted to keep it proprietary, but it was reverse engineered by using side channels and subsequently attacked. And you will be surprised to know that it just requires one trace to break the key lock cipher. So this is an example of what is called as an SPA attack. So therefore, let us see how the power trace looks like. You can see here how the power trace of a round of AES looks like. So in particular, you can see that in the left diagram, you can see that there are 10 sort of jumps, right? And if you count the jumps, you basically have an idea about the fact that it has got AES 128 implemented in it. and therefore it has got 10 rounds of encryption operation. So you observe the variation of the powered values, and you can see that, like if you just see this power trace, you typically do not have a way of understanding what is the secret. So therefore, a classic AES 128 is probably not vulnerable against what is called as a simple power attack. But what you can do is you can zoom in further. So the right trace you can see is a zoomed in version in one round, and you can see that there are still variations inside the round. Like at the beginning, you can see that the variation which is there are typically for the sub bytes of AES and followed by the other parts of the AES algorithm. So these variations occur because of the fact that the power consumption depends upon, also upon the data. That means even if you keep the same, if you're varying the plain text, right, and then your data is varying, then even if it is the same operation, that is suppose the sub byte operation of AES, you will still find a variation in the power trace, and that variation is what leads to a differential power attack, or what is called as a DPA. So here are some traces of a DPA algorithm. So you can see that these are trace for, say, the DES algorithm, and like somebody the 4,000 power traces. You see that you can distinguish the correct key from the wrong key. This is another sort of angle of seeing the same stuff. You can see that the correct key is, say, 4.1, which has got distinguishable spikes to be distinguished from the wrong keys. I have not talked about the technique of doing it, but I'm just trying to kind of first of all motivate that how DPA works, and these are examples of showing that DPA works on virtually any algorithm that you can know of, because the attack really doesn't target the algorithm, but it more or less targets, more targets the implementation through which it has been done. So then let us try to understand, like how a CPA works. So here is a very simple illustration of CPA. And like if you concentrate at this point, right, then you will probably understand the basics of how this power attack technique works. So you see that what we do is we take a bunch of plain text or ciphertext, depending upon the fact whether you are attacking an encryptor or whether you are attacking a decryptor. So say I'm assuming that you are attacking an encryptor. Okay, so you take, say, a bunch of plain texts and you encrypt them. And suppose I encrypt, say, D plain text, and I get the corresponding ciphertext. Okay, so therefore, right, I mean, right now what you do is you have got, say, like D encryption which is being done. So you have got D ciphertext. Okay, so now what you do is you take the cipher, and you know that in the last round of AES, for example, there are, or rather I would say AES 120 in particular, there are 16 bytes. Okay, so this, so you know that there are 16 bytes of the key, and I want to recover the entire 128-bit secret key, but I can engage in a technique which is called as the divide and conquer technique, which means I will not guess the entire 128-bit key at once, because that is simply not possible because of the 2 to the power of 128 possible search space, which is huge. So what I rather do is I try to kind of recover the key in a byte by byte fashion. So let me recover the first byte, then the second byte, then the third byte, and so on. If I do this attack in this manner, then my complexity will be 2 power of 8, right? Because one key byte can take 2 power of 8 values multiplied by 16, which is still manageable amount of guesswork in the worst case. So now what I do is I will just show you how to recover one of the bytes of the key. So let me, so here we talk, like we denote that by what is called as the key hypothesis. So suppose there are k hypotheses of the key byte. So in this case, for AES 128, there are 256 possible key bytes or key hypotheses which are possible. And then you take all these ciphertext. Okay, so I'm talking about attacking the encryptor. So I have been given this D ciphertext. I take this D ciphertext, and then what I do is I take a key hypothesis, and then I do a decryption of only one round of AES 120. That means I go back one step behind the last round. So now note that since I'm operating only on one byte, I do not need to bother about the other parts of the algorithm, but I just do one part, which is the inverse S box, and then I go to the input of that S box. Okay, so therefore I again get a byte, right? I get a byte corresponding to a given key. That means suppose I take D1, I basically, my hypothesis is say K1, I XOR D1 with K1, and then I compute the inverse S box of D1 XORed with K1, and I get a value which is called as the hypothetical value, say V11. Okay. So likewise, I, I mean, for this particular cipher byte, I do it for all the key hypotheses. That there are k hypotheses, so I do it for all the k hypotheses. And since it's a like a bijective map, I get k possible values of that. So I get k possible values of like which are denoted as V11, V12, and so on till V1k. So likewise, I do this for all the D ciphered bytes, and therefore I get a matrix whose number of rows is D and whose number of columns is K. So it's a D cross K matrix. And then I have got, what I do is I basically apply something which is called as a power model. So power models means it's a very popular terminology in the VLSI community, which says that I would like to predict the power consumption, or rather the dynamic power consumption of a computation. And usually it is kind of approximated by, say, the Hamming weight of the byte. So suppose your Hamming weight of V11 is, say, 3, then Hamming weight means the number of ones in the byte. Then you denote that power or the hypothetical power by the value or integer value 3. Likewise, you can have got Hamming weights which range from 0 to 8. There can be 9 possible Hamming weight values. And therefore, these are essentially denoted by in this hypothetical powered matrix. So you see that your hypothetical powered matrix has got D rows and has got K columns. But then when you are observing this or you're calculating this hypothetical powered values, you along with it, right, you also have something else, right? What is that? You have the side channel information. And the side channel information is the power trace which has been captured, okay, by your experimental setup. So this is the power trace, suppose, which you have captured, which shows the plot of the voltage, say, with time. And that also is kind of, like sort of represented in the form of a matrix. So remember that you have got D encryptions which you are doing. For every encryption, you get a power trace. Okay, so the first encryption, you get a power trace. Second encryption, you get a power trace. And like this, for D encryptions, you get D power traces. Okay, and remember that you are sampling it, right? You are sampling it at, say, T instances of time. And therefore, right, every power trace will have got T values, T sample values. And therefore, all these T sample values, which are actually real numbers, are now denoted in this matrix row, which is from P11, P12 till P1T. So likewise, we have got a matrix whose number of rows is D and whose number of columns is T. So that is what I called as, say, the real powered matrix. And this is your hypothetical powered matrix. So now we, like input that to a statistical analysis technique, which is nothing, say, but, like you would like to correlate these columns with the columns of your hypothetical matrix or a hypothetical powered matrix with the columns of your real powered matrix, with the idea that if, right, your guess of the key was correct, remember that the column of the hypothetical powered matrix depends upon the key hypothesis. Okay, and if your key hypothesis is correct, then there will be some instance of time when you will find that there is a peak in the correlation. Okay, and therefore, right, in order to observe that, you again compute this matrix, which is called as the correlation matrix, which is nothing but any value here. Like suppose I take R11. R11 means it's the correlation of the first column of your hypothetical matrix, which is this row H11, which is this column H11, H21, likewise to HD1, with the column of your, or the first column of your real power matrix, which is P11, P21 till PD1. So this correlation is observed in R11. Okay. Likewise, you create this matrix and you find out that if there is a peak, then you, like suspect that your candidate guess was probably a correct one. And that is how you distinguish the correct keys from the wrong keys. So this is a very, I would say, like a high level description of how a CPA works or a correlation power attack works. And this is some more details, but essentially the same idea. So you can see that this is your hypothetical power matrix, and this is the real power matrix. You take two columns here, and you basically correlate them, and that's the observation. That's the correlation value which you kind of note in your correlation matrix. So therefore, right, in order to sort of illustrate this, we build a tool in our institute, and we also have an incubation based on our on our lab, which we called as embedding security and privacy. And this is a tool that we have built which works on open source platforms. It combines analysis for both power and fault attacks. It's built on Python and therefore virtually works on most of the platforms. It also can be controlled remotely. And I particularly highlighted because, like remote control is a very important thing as we are seeing in the present day situation. So that was a kind of brief overview behind CPA or power attack. So let me try to give a little bit of background behind what is called as a fault attack or differential fault analysis. So in differential fault analysis, what you do is you take your plain text, you apply an encryption algorithm, you get a fault-free ciphertext. But in a DFA, when in the second instance, right, when you are again observing your or obtaining your ciphertext, you try to kind of perturb the like environment. So you try to kind of create maybe a change in the voltage line or the clock line in some simple setups, or you can also try to do more sophisticated injection techniques, like maybe like shoot an EM gun, and like maybe you can also try to do something more fancy by taking maybe a laser gun and then shoot, right, and that creates a fault. So therefore you get a faulty ciphertext, and now you would like to kind of analyze the fault-free ciphertext and the faulty ciphertext and try to obtain the secret key. So this is the basic idea behind how this technique works. So I will try to kind of give you the idea about how you can do a DFA on, say, the AES algorithm. So here is the very popular AES 128 algorithm. In particular, I just show the last few rounds. So I start from the 8th round byte sub or sub byte operation, and imagine that there is a random fault which has been introduced. Now, because of this random fault, right, you know that it's a random fault, which means you have got no idea about what this fault value is. It can be anything, okay? So now when you apply the S box, then it basically gets transformed into something else, say F dash. And again, subsequently, if you apply the shifter operation, it still remains in this location. And now when we apply the mixed column in AES, you know that the mixed column in AES is a multiplication by a constant matrix in Galois field GF to the power of 8. So when we apply the matrix, then this particular differential, or I would say like the fault, essentially gets sort of spread out by demonstrating some interrelationship. That means now, although initially, right, this particular byte could have taken any possible value, this particular differential could take on any possible value, but now it imposes a constraint on this column. So you see that this column, the first column, right, at the output of the 8th round mixed column, ideally should take 2 to the power of 32 values, but now because of this fault can take only 2 to the power of 8 values, because F dash can take 2 to the power of 8 values, and depending upon F dash, this column has got a fixed value, right? 2F dash, F dash, F dash, and 3F dash. So the entropy of this column reduces from 32 bits to suddenly 8 bits. And that essentially is, like the reason why a fault attack can work. So now if you go ahead, right, you will see that there are more diffusions which are being shown here. So in the most naive form of DFA or differential fault attack, what is being done is you guess the last round key and you try to go back, work behind and go to this output of 9th round mixed column and try to exploit these interrelationships which are being shown here, like with F1, F2, F3, and F4. You see that these are the interrelationships which are possible, and you try to kind of apply this to form equations and solve them in the best possible manner and try to get the key as fast as you can. So in a very naive manner, you will see that you probably would require 2 faulty ciphertexts, and that would reveal the key, exact key, with a probability of almost 1. Now, there are some more improvements on this basis, on this basic technique, which I'm not getting into for the sake of time, where you try to kind of exploit, I would say, a little bit a vulnerability in the AES key schedule, or I would say rather a property of the AES key schedule, through which you can actually do this attack with only one single fault. That means with only one single fault, you can reduce the AES 128 key value to only 256 values. And you can also do another interesting optimization, which will kind of make the attack 4 times fast. Like in the naive technique, the attack has got a complexity of 2 power of 32 AES operation, but you can reduce it to 2 power of 30 trials. So that small improvement, right, actually can be quite interesting, because you see that if you are taking now, initially if you are taking 4 hours to do an attack, now you will just take 1 hour to do this attack. So that is the basic, I would say, like the idea behind how a DFA works. And there are many, I mean, the fault attack in particular, right, is becoming more and more important, because of several developments in how the crypto chips are being implemented nowadays. Okay, so here is an example of a fault injection attack being done on a real life automotive chip. So you know that in modern day, the car that we have is probably more of a computer than a mechanical equipment. There are, like several lines of codes which are being written in a car, and there are many safety measures which are being taken in the car. So ISO 26262 standard is a framework for development of safe automotive electronic systems. Right now, people are developing security standards, and there are, just now I was going through some of the documents, and it's interesting that how people are trying to understand that safety and security are not the same. But I will try to kind of give a motivational example, which I essentially was happy to be a part of, which basically talks about the fact that if you take an ISO 26262 standard, which essentially recommends to apply standard reliability techniques for protecting against fault attacks, we try to kind of motivate here that those are not adequate for protecting attacks like fault adversaries. So there are techniques which are being present for in the reliability community, which are, I would say, like protecting against what are called as natural faults. But remember that when you're talking about adversarial faults, then the adversary is more motivated, right? Because he's more clever and he can direct the fault injection to a like direction where the classical redundancy check can completely fail. So let me give an example. So here we talk about two chips which are called as ASIL-D chips. So ASIL-D is a certification which shows that it has got a high level of reliability or safety mechanism being implemented. So it is an ARM Cortex R4 chip, and there is another one which is called as ASIL-D2, which we also present in this case study, which is a PowerPC based chip. And these are two of the most prevalent architectures in the safety electronic industry. In both these targets, mechanisms have been implemented, which are essentially nothing but a dual core CPU. And why do you have the dual core CPU is, of course, you can do it for performance, but here the dual core is rather used for a simple time redundancy check. That means you do the computation twice and you compare your result and you compare in memories with your, so there is an error correction which is also being implemented. So the error correction is implemented using, say, usual parity bits, and you do a comparison to check that whether there is any fault inside the when you're doing the computation. So we use two tools for fault injection. So we use a voltage glitcher. So we use a glitch-based voltage injection tool. We also use an EM glitcher. That means we use an electromagnetic gun, and using the electromagnetic gun, later on, if we have time, then I will show a video for that. And you can see that if there is an EM gun, then with the EM gun, you can shoot EM pulses, and that essentially can lead to spikes in your electronic circuit, which will get manifested as faults. So what we do here is we target a pin to trigger the glitch generator. We take this pin from the device, and then we trigger the, like the pulse to create the fault. So we do two experiments. One of the experiment is, the first experiment is we essentially implement this simple assembly in the ASIL-D chip. So you can see that it just adds the assembly instructions for adding, say, 1 to the intermediate register. And then you basically, send this data over the serial channel. And that is, so what you basically want to see now is that there are some, say 100 additions that you are doing. So at the end, you would really, if the computation is correct, you know that, say, 100 should be essentially what is serially being transferred. But if there is a fault, and the fault essentially, say, bypasses an instruction, or rather skips an instruction, which is very common, by the way. Like if you take an EM gun, then you often see that either the instruction is skipped, or even in some cases, right, the instruction is modified. Like suppose you are doing a multiplication, the multiplication probably ends up in doing something else. It doesn't do a multiplication, but maybe does an ANDing operation. In the second experiment, you have got an authentication check. So the idea here is that you basically have got, so typically, right, for most of these chips, there is an authentication which is being in place. So you can see, if you see the code, you verify that if the flag is 0, so then you send serial authenticated information, else you deny it. That means if the authentication fails, then you deny computation, you deny the access. So what we see here in experiment 2 is if you can introduce a fault and the fault bypasses the authentication check, then we would call it as a as a fault being still be prevalent on this design. That means the redundancy check that is being present in the device doesn't work to essentially protect against these class of faults. So here is a sort of snapshot of this result. So in ASIL 1 and ASIL 2, you can see that for the first experiment, which we call as the unroll experiment, with a voltage injection technique, 87% of the faults were not detected. Whereas in the ASIL 2, in the authentication check, you can see with the EM way of injecting the fault, 57% of the time we were able to still bypass the check which was being present inside it. So this shows that like the fault still works, and we did a postmortem because nobody will really tell you exactly why the attack works. So our postmortem is like something like there is as I said, that there is this like double code which you are using for doing the computation. So we found out that it may happen that a possible analysis is that the glitch that you are introducing is affecting the same instruction but in different stages of the pipeline. So suppose you're doing a fault injection which is affecting a multiplication, but the multiplication, right, I mean, you see that you are doing a redundancy check, which means you are doing this computation twice, and that means that since you have got two cores, you are basically like using both the cores for doing your redundancy check. Now when you're introducing the fault, the computation is present in like both of these cores, but maybe at different stages of the pipeline. And what is happening is that because of the fault, these two different the same instruction in two stages of the pipeline are getting affected, and therefore they're resulting in similar outputs, and therefore they are completely being missed by the detection strategy. So this particular experiment is kind of showing us that we need dedicated techniques for protecting against fault adversaries. So let me try to give a like a demonstration of hopefully it will work. So I would, so this is just to show you about the setup, but more importantly, I believe that you can see the fault here. Like when the fault takes place, then there is a change in this value, which was initially 1.5, but now you can see that it gets corrupted to 9.5. So this just shows you how the fault works when you have got an EM setup, and subsequently you can utilize it for your fault analysis. So so that was my, like the second part of my talk. And I will, with the remaining part of the talk, I will be talking about this idea of physically unclonable functions and how we can use it for authenticating for the things in the context of IoT. So so let me, as we have already understood, right, that we know that IoTs has got virtually no protections against attacks. And so now what we try to kind of look into is whether we can actually develop techniques for protecting IoT which has got very low overhead. That means the, like the computer, of course we need protections against sidechain attacks. And the idea is that if you really want to protect against sidechain attacks, you need countermeasures, and the countermeasures are costly. So at the end, we need to design low overhead techniques which can work on resource constrained environments and essentially can operate in such situations. So I already talked about this Philips lighting system and how we can, attack it. So in one of the attacks that we developed in our laboratory or in our IoT laboratory was, like if you go into the authentication technique which is being used in these lighting systems, it turns out that what they initially were doing is they were developing a, so we all know that the devices will have a corresponding MAC address. So they were applying a very popular hash function, which is essentially at that time MD5, and then they were using it for whitelisting. So we found out later on that this mechanism was changed, but it became even more worse. Like now the communication was done in the plain text. So this vulnerability we were able to detect by using a tool which is called as Wireshark. And we found out that, like it was basically when it was sending a command to the breach, then it was basically generating a random number and it was communicating over the clear. And that essentially can be captured. And we were having some nice experiments of, like your bulb can be controlled by your neighbor if you had a bad fight with he or she. So that basically shows us that many of these conventional IoT devices does not have proper authentication mechanism. And one of the reason is cost, because we really cannot engage a very, like costly algorithm, which is hard to implement, and that will shoot up the IoT product's price, and that will make the entire product not tenable. So therefore, right, I mean, one of the ideas that we try to look into is whether we can have a keyless crypto protocol or crypto mechanism wherein we can use this promising hardware primitive, which is called as physically unclonable function, to secure the IoT devices. So I will be trying to kind of give an overview behind what is a PUF. So the PUF essentially is a very promising hardware fingerprint, you can say. That means, like, ideally, if you have got two devices and if you implement the PUF on both these two devices, then it should give responses which are essentially statistically independent of each other. So PUF in that sense has got, I would say, like it's a primitive or a hardware primitive which essentially has got upfront identification inbuilt in its very design. But then there are many challenges in terms of PUF design. For example, one of the biggest challenge is that the PUF needs to be reliable. That means, like the same randomness that you are trying to exploit in the PUF to give you a unique authentication can also make it unreliable. That means if you are taking a PUF and applying an input at different time instances, it may end up in giving different responses, which you don't want. You also want to ensure that the PUF's response doesn't vary with your temperature, with your humidity, and so on. So you need to make the PUF reliable. Along with it, you also want to make the PUF resistant against what are called as model building attacks. So what are model building attacks? Model building attacks are nothing but something like techniques which, as you can see that the name suggests, it's a physically unclonable function, right? So that means you should not be able to predict the response for a challenge which you have not seen. But then people have tried to develop techniques which are essentially assisted by many of the popular machine learning techniques, which essentially tries to develop mathematical models for the paths. So the idea, right, is that the path has to be an unclonable device, but then using powerful machine learning adversaries, if you're able to learn the responses for new challenges, then it breaks the original promise of a path, right? And therefore you need to make your path reliable and also model building resistant. So therefore, right, I mean, taking a closer look at the path basically is nothing but like a Boolean circuit, but it doesn't implement it by a Boolean mechanism. Okay, so that means it implements a Boolean. The path circuit is, like maybe a bunch of hardware tools which you have implemented, and it doesn't have a closed form expression of expressing the response as a function of the input. So if you take the path and apply a challenge, maybe an n-bit challenge, you get an n-bit or m-bit response. Okay, and that is essentially how what is called as a challenge response mapping of the path. So ideally, the path should be unclonable. That means if I take two devices and if I apply the same challenge to these devices, then if I tell you what is the response of one of the device, you should have no easy means of understanding what is the response from the other device. Okay, that means the two responses should be statistically independent. But then the basic idea of path is very promising, and it has got its source of variations in the MOS device, in the device physics, and so on. And if you just see the basic promise of a path, then the path really is a very, like a fascinating concept, in the sense like it gives you very interesting variations which can be exploited by security protocol designers. So here is an example of how so we take a ring oscillator. So it's a ring oscillator is a very popular electronic circuit, which typically has got, like an odd number of inverters which are being connected in a feedback. The idea is that it creates an oscillation frequency. So if you take the same device and if you implement it in an FPGA, so here I show 4 FPGAs, you can see that the frequency which you derive, right, is not constant. There are small variations in the frequency, and the variation essentially is dependent also upon the XY coordinate on which you are citing the particular ring oscillator. And also if you take 2 FPGAs, you will find that there are differences in the arrow frequency, and it's kind of unique. So that means if you take this snapshot of one of the FPGAs, then you have a mechanism of getting what is called as a device fingerprint. So the idea is that this unique behavior can be utilized to develop a device fingerprint which can work as a very seamless mechanism, I would say a keyless mechanism of getting what is called as the fingerprint of the device, and can work or serve as an identity of the device. So therefore, as a security primitive, it can reduce cost, it can raise security. In a world without path, you need to store the key maybe in a non-volatile memory, and that also opens up several opportunities of sites and attacks and so on. On the other hand, in a path, there is no key. The device itself works as the key, okay? And the device never really leaves the IC. It kind of is inside the IC, and virtually after encryption process, it is not there. So it is kind of deleted from the environment. But at the same time, as I said, that there are many design challenges for path. The idea, of course, you need to make the path unique. Uniqueness is an important property, but along with it, you also need reliability. You need uniformity of the path. And so this is the classic way of how you can, engage a path. So the idea is that you take a path, and suppose you want to authenticate the path, and the path has got a challenge response. Remember that suppose there is a thing in the Internet of Things. So maybe it's your Philips lighting system which has got a path now, and you know that the path, if I give a challenge, it will give me a response. But how do you know that whether that response is a legitimate response? So because of the very fundamental definition of a path, you cannot have a copy of the path at your end when you are doing verification, right? So what you can therefore do is you can have a database where you store the legitimate challenge responses of the path. Now remember that if you have got a path which says 64-bit challenges, you cannot store 2 to the power of 64 challenges and responses. So what you do, probably you store a subset of this challenge response database, and every time you apply a challenge, it gives you a response. You verify whether the response matches with your table. And if it matches, right, then you allow that device and you treat that device as an authenticated device, or you disallow that device. But remember, in this particular setup, you need to ensure that you need to keep in mind that this challenge and response has also been seen by the adversary who is monitoring this challenge, this channel, and therefore you cannot reuse this challenge response. So once you have used it, you have to strike it off. And that is why these class of paths are essentially called as strong paths. Okay, and why strong, I will just tell in a minute. But the idea is that it has got a very large challenge response or challenge space, because since you are removing the challenge every time your number of challenges, right, is getting reduced by 1. So you need a large challenge space in order to really implement this for practical purposes. Now, why it's called a strong path is because since the adversary is seeing the challenge and also the response, the adversary should not be able to predict the challenge or the response of a challenge which he is not seeing. And so in order to break this guarantee, what the adversary can do is it can try to develop a machine learning model or a model for the path. And this is what I meant to say, that the path has to be model building resistant. That means it should not be, like by seeing a bunch of challenges and responses, it should not be opening up, it should not be diverging its model, which reveals what is the response for a challenge which has not yet been seen. And therefore, what is important is that the path has to be strong against machine learning attacks. And that is what probably says, means by saying that it's a strong path. On the other hand, there is another category of path which is called as a weak path. The idea is that it is only used for generating a secret key, and the key is never being seen by the adversary. So there's a different class of paths which I will not get into, which essentially there are some paths like what they are called as SRAM paths and so on, which essentially are used only for generating the keying material. Okay, and these are called as weak paths. The weak path, the challenge space can be small simply because it doesn't have this problem that I just mentioned. On the other hand, it is more challenging actually to develop what are called as this strong paths, which also needs to be machine learning resistant. So in the naive authentication, there is a limitation that, as you can see, that the bare CRP or the challenge response pairs needs to be stored somewhere. And if by any means the adversary can collect the CRPs, then she can imitate a legal client. So therefore, right, we need to develop an authentication using path which doesn't store the challenge response in a naive manner. So here is a part of a project that I was involved with with one of the companies which are trying to kind of have paths for IoT devices. So in our protocol, we have got two phases. The first phase is an enrollment phase. Suppose that this device which has got the path tomorrow wants to communicate with a verifier, which is a verifier S. Okay, and the verifier S, since it's typically a server, has got a secret key which is stored in some kind of tamper-proof memory. But this device, right, doesn't have any secret key. It has just a path inbuilt in it. But remember, this device cannot have a copy of the path because the path is unclonable. So what we do, therefore, is we enroll this device to a security credential generator at the beginning of the protocol, wherein the credential generator sends a challenge and it obtains a response, and the response is being hashed. And suppose I denote it as PA, and the corresponding secret key of the verified S is also hashed by another hash function along with the challenge, which is say CS, and we obtain say two parameters PA and PS. Now what we do is we also kind of combine this protocol with an elliptic curve protocol where we do a scalar multiplication and we compute something which is called as a parameter B. So now we take this CA, CS, and we store it in the pervasive cloud. And along with it, we also store these two parameters, the secret parameter, the random parameter A, which is being changed in this computation, and also this parameter B, and we keep it in the cloud. The idea being that since it's a cloud, it has got a lot of memory probably available, but you also need not bother about the secrecy of this data. So it can be accessible by any party for that matter. So now once we have this set up, we can go into the authentication or verification phase. So now suppose the verifier wants to communicate with this node A, then what the verifier does is it again contacts the cloud, gets this information CA, CS, A, and B, and note that what it does is it applies it because it has got its own secret key. So it can compute one part of this information, which is PS, and then again apply this A and B and apply this elliptic curve operation and get the value of PA. Now note that we assume that since this secret key case is only available with the verifier, this information is obtained by the verifier and not by the adversary, and therefore the adversary cannot obtain or cannot get the value of PA, because PA either needs the secret key or it needs the path, and the path is assumed to be unclonable and therefore unpredictable by the adversary. So now what we do is the verifier does is it calculates, it generates an ephemeral variable which is X, and computes a challenge which is QA, and a corresponding like paired output which is the expected response which is a VA, and sends this information to the node A. Now note that the node has got its own path, which is the legitimate path or assumed to be the legitimate path, and therefore computes this R1. And now since it has got this information of PA plus XPS, it can obtain PA by, or rather it can obtain XPS by using the information of PA, which the node can derive using its own path. So now once it has got PS dash, which is nothing but XPS, it can compute the value of VA dash by applying this pairing computation, and it's basically being sent back to the verifier. So this entire protocol which we have has been implemented on a device, and it works on actual IoT devices. So here is an example of that, where we basically initially hack a video surveillance camera, which doesn't have typically an SSL protection, and then we show how it can be, I would say like augmented with a path design to prevent standard meet in the middle attack or replay attacks which are possible. So here are some like snapshots on whether the path really fits a budget. You can see that it consumes very less power, something like 0.0044 watts, and it works on standard elliptic curves. We basically choose this elliptic curve, which is a 512-bit prime number based elliptic curve, and essentially perform our computation, which takes a latency of something like 480 milliseconds. So here is, before I conclude, here is a snapshot of how the PUF, or a demonstration of how the PUF works in real world. And there is a very famous attack recently being proposed on WPA2, which is a wireless protocol, which is called as crack. This is an example of a replay attack, and we show how the PUF can be utilized to protect against this attack. Right. So this is a demonstration of showing how in real time, right, your path can be utilized. So note, I would like to point out that in this particular protocol, although we have an elliptic curve protocol being in execution, but at the end of the node, there is no secret key which is being stored. So it is a completely, I would say, in one sense, a keyless protocol which is operating. So, so that essentially brings me to the concluding slide of my talk. So I try to kind of show that security of IoT is of utmost importance in modern society. We need to develop expertise in several domains like security, embedded systems, VLSI architecture, networks, ML. All of them are important simultaneously, certainly. And we know that IoT constituents are varied. So we need resource constraint things at one end, there is a pervasive cloud on the other end. So we need and all of them offers different attack surfaces like sites and attacks, inability to support costly ciphers, eavesdropping, replay, masquerading, poisoning, and so on. I would also like to kind of mention that the fault attack, right, that I've been working probably for quite a sufficient amount of time. And it is interesting to see that now people are trying to and working, like are being able to do fault attacks which are working on actually on servers also. Like for example, there is a famous bug which is called as Rohammer bug, which essentially works even on computing systems where they can show how they can fault a DDR or DRAM chip to create faults. There is a recent paper which has been published to show how a fault attack can work on GPU machines as well. And all of them are on real life scenarios to show that how they can work on modern day systems. So what we strive is to develop novel tools and solutions for side channel security, design new hardware primitives for end-to-end and IoT security. So at the end of the day, I would like to conclude with this famous saying which says that the chain is no stronger than its weakest link. So if you really want to develop secured IoT solutions, then we have to keep the heterogeneous nature of IoT in our mind and try to develop end-to-end security aware designs where engineering is extremely crucial to really have an end-to-end security. So I know that since we have got many in the audience, right? If there are people who are interested for pursuing or joining us, then we have our advertisements which are being regularly being posted at this website, which is shown as www.itkgp.ac.in under temporary jobs. So for example, we recently have a project on designing and implementing on efficient and secure searchable encryptions sponsored by MHRD STARS. And there's an application deadline of 11th August. So if some of you are interested, then you can shoot your or maybe apply online. There's an online portal for that. I would also like to try to take your like attention towards what we call as security privacy applied crypto engineering conference that so this is the 10th time that we are doing it in India. And we have a proceedings in Springer LNCS. Selected papers are invited to the Journal of Hash in Springer. There's a deadline for this in 7th August. So if you are interested, then you can definitely, you are most invited to submit papers. It is co-located with another conference, international conference that we are doing in India actually. Well, we wanted to do in India, but now everything is virtual. So it will be done also in the same time in December 2020. So for people who are really interested for more discussions on hardware security, so there is an NPTEL course that I offered and I'm still trying to offer. So you're most welcome to attend this course, which has got a 60 lecture discussions on various facets and topics on hardware security, starting from basics to I would say pretty advanced topics on hardware security. So with this, I would finally like to thank you for your attention. So that brings me to the end of my talk.
Thank you so much, sir. There are a few questions in the chat box. If you want, I can read them for you.
Okay, let me see. So maybe I could stop sharing.
Yes, sir.
Oh, I see 66 questions actually. So For the sake of time, will probably
So you can take the most recent one.
okay. Mm,
I request the participants to post questions.
so so since there are many questions which I really am thankful for, I will try to just read out few questions from the end actually. So it's there is a there are some questions on blockchains. Actually, I personally do not really work so much on blockchains. There is a paper that I was involved with, so I would request you to maybe have a look at that, where we try to apply blockchains for securing the supply chain in particular, where we try to combine the blockchain with a puff. So if you go into my, maybe you can send me an email, then I can respond to this. And there is also a question about in which areas puffs are being used. Well, puffs are being used nowadays in various places. They are also commercially being deployed. There is a company which actually also, there are many companies which are now developing puffs. In particular, I was attending DAC just 2 days before, and I found that even Intel, for example, is that has now kind of procured this company called Altera, and so they are also developing puffs both on FPGAs as well as on silicon. So that means like if companies like them are deploying puffs, then I would expect that puffs are being at least promising to be used in area. In our case, we were trying to develop a puff for an IoT application. So there are questions on puffs being applied in other places like banking systems and credit cards and so on. So in particular, I believe that if we can really solve the reliability issue of puff, which we have actually to a large extent, then I believe that there will be more promising applications for puffs. So, so in one sense, yes, I mean we can, but of course, uh, I mean, uh, we need to engineer the puff also in a proper manner. So there are many other questions actually. Maybe I.
Yes, sir. So one of the participants is raising hand. I would like him to unmute Dr. Rajendra and please ask your question.
Sure, sure. I think that is best. Yeah, please.
Sir, I have one question. In which of the area the puff is mostly used?
Right. So the puff, largely, I would say that there are two types of puffs. Okay, like as I said, weak puff and strong puff. The weak puff is actually used for like generating the initial key. So now these kind of puffs are being used for several things. Like one of the applications I can tell you is about like having secured boot, for example. The idea being is that they try to use SRAM puffs for generating the initial configuration, which essentially will be device specific, and could be a mechanism of implementing what is called as secured boot. So likewise, there may be other applications of puffs also. Like for example, as I mentioned, that if you take typical IoT applications, then a puff can be utilized for those kind of applications as well. Like suppose you take a smart camera, for example, and you really want to have an authentication in the camera because you know that the camera or the video camera can be attacked in many ways because of inadequate authentication. And if there is a situation that you cannot really apply a very complex cryptographic protocol on such kind of embedded systems, then puffs can be handy for such situations.
Thank you, sir.
Yeah, thank you so much, sir. If there's any other question, I request participants to raise their hands. Serial number 330. So please unmute.
Hello, sir.
Right.
Hello.
Yes,
Hello.
sir. Please ask your question.
So my question is, at the chip level, can we use PUF for component level security? I mean to say, if we source components from different vendors, we don't know which are genuine and which one are not, right? So if they mix some malicious components into it, can we identify them and give security at the chip level?
See, I mean, there are two problems. Okay, so puffs are typically, I would say, better suited for authentication, for identification. Okay, But if you are asking for whether, like a component has got malicious components inbuilt in it, then that's a different problem. It's kind of identifying something which are called as Trojans, okay, inside it. So that I would say requires other techniques. But what you can do is by I would say coupling a puff with a device, you can make the device seller accountable for his design. Because the fact is that the response which is being provided by that device becomes specific to that design, to the device owner. Okay, so that way you can make him or her accountable for what he is giving. Okay.
Thank you, sir. Thank you.
Thank you, sir. Okay, we can take up the last question. Can we use the puff for image authentication using smart camera?
Yeah, I mean, in my opinion, you can use the puff for any authentication actually. So in one sense, I mean, I'm not an expert in image encryptions and image authentication, but what I can kind of at least say is that the puff can be used for identification of the camera. Okay, so you see that the way we are using the puff, right, is not really depending upon the data that you are processing, but it is more like trying to connect it, or like making or deriving a unique fingerprint for the device. So in this case, the device is your smart camera. So yes, you can use it.
Yes, thank you so much, sir. I request Dr. Indivar Gupta to extend a hearty vote of thanks to Professor Devdev.
Hello.
Yes, sir.
Yes. See, generally, Professor Devdev, he always give very wonderful talk. So of course, it was expected that he will go very informative and wonderful talk. And this talk was actually physical realization of crypto product, crypto. See, people can see that how this cryptology or cryptographic chips are being used in different kind of products and IoT. So let us give big thanks to Professor Devdeep for giving very excellent and informative talk.
Thank you so much, Indivar, for the kind invitation.
Thank you, sir. Thank you, Professor Devdev, for such an enriching experience throughout the session. Thanks a lot.
Thank you.
So here we have a break of 10 minutes. Then we can begin with the next session. Please join again for the next session. We'll begin at Indivar, sir, 11:30 is fine?
Yes, yes. I'm ready. Okay. I can come at any time. No problem.
Okay, sir. We'll begin with the next session at 11:30 sharp.
Bye, everyone. Bye, everyone.
Hello.